Hi, I'm Kumar Kahadapitiya, and today I will tell you how to model long-term motion efficiently. First, let me show you what we propose and why it is important. We introduce a learnable frame selection method and a fusion method between multiple temporal resolutions. As for the benefits of our method, it achieves a new state-of-the-art performance in activity detection. We do this while being more than one order of magnitude efficient compared to the previous state-of-the-arts. Plus, we do not need to rely on any additional input modalities, in contrast to previous methods. We are motivated by the challenges in representing long-term motion. Although a video model can benefit from modeling long-term motion, naively doing so has some drawbacks. 1. It needs more compute. 2. Even if we have enough compute, it is extremely inefficient to process redundant data, particularly in untrimmed video sequences. For instance, in this sequence, there are multiple frames which are essentially identical. One solution is to process input sequences in a lower temporal resolution, similar to what slow-fast is doing. However, working with fixed temporal grids does not solve this issue with redundant frames quite yet. What we need is a non-uniform temporal sampling strategy to filter important frame locations. In such a setting, the uniform order between these frames will be broken, and it requires an emphasis on temporal alignment when fusing such representations from multiple streams. So how do we address this? We propose coarse-fine networks. Given an input sequence, we create a coarse stream by temporally sampling important frame locations based on the proposed grid pool layer. However, we infer predictions for every frame following the associated grid unpooling operation. We create a secondary stream which looks at a longer temporal range to extract a fine-grained long-range context. The proposed multi-stage fusion then fuse these representations from the two streams with proper temporal alignment. Let's look at the novelties of our method in detail. Grid pool is a learnable temporal sampler. Given an input xc, we project it to a set of confidence values pi corresponding to different temporal segments. The idea here is to sample high confidence regions with a low sampling duration, which means the complement of these confidence values are linearly proportional to the sampling duration. We use this idea and select non-uniform sampling locations from the corresponding CDF. Using these locations as a temporal grid, we resample the input through interpolation to select important frame locations. This process is differentiable and hence end-to-end trainable with backpropagation. Multi-stage fusion works on three aspects: filtering, aligning, and using multiple abstractions. Given the two streams, first, a self-attention mask filters which fine-grained information should be passed through to the coarse stream. To perform alignment, we use a set of coarse-centric Gaussians centered at each coarse frame location to weight the fine-grained information accordingly. Finally, the information from multiple abstractions or multiple depths of the network get concatenated and projected as scale and shift parameters to augment the coarse stream. Let's look at some key takeaways from our ablations. Fusion benefits from multiple abstractions. Rather than late fusion or one-to-one intermediate fusion, we see a clear improvement when considering multiple abstractions to augment the other stream at a given depth. Learned frame selection outperforms max pooling, average pooling, or striding. Proper temporal alignment and filtering are definitely important when fusing different temporal resolutions. We see this when comparing against a slow-fast variant with the naive fusion method. Thank you for your attention, and if you have any questions, join our live Q&A session. Our code is available online.